Hi Year 11. This is the topic of probability for the International Baccalaureate DP courses, Analysis and Approaches, and Applications and Interpretations. In this topic, we're going to cover set theory, laws of probability, conditional probability, independent events, and Bayes' theorem. And in this first lesson, we're going to look at set theory. So let's begin. A set is a collection of objects. So for example, the set A contains the elements 1, 2, 3, 4, and 5. And the set B contains the elements red, yellow, and blue. Now we use capital letters to name the sets. The number of elements in a set is written as n and then in brackets the name of the set, in this case A. So for example, if A is the set that contains the numbers 1, 2, 3, 4, and 5, then the number of elements in the set A is 5. We can write that 1 is an element of A. We can also write that 6 is not an element of A. The null set or empty set has no elements, and it has the notation open and closed curly brackets with nothing inside, or a 0 with a /. Now all numbers are members of the set of complex numbers, which has the symbol C. And you're going to learn about complex numbers in the high-level course. Within the set of complex numbers, we have the set of real numbers and the set of imaginary numbers. Within the real numbers, we have got rationals and irrationals. And inside the rational set, we have integers, and inside the integer set, we have natural numbers. Okay, let's have a look at all of those sets of numbers in more detail. So C is the symbol that we give to the set of complex numbers. Complex numbers will contain a real part and an imaginary part. I is the set of imaginary numbers. And for example, lowercase I is equal to the square root of -1. R is the set of real numbers, which means that they can be plotted on a real number line. Q is the set of rational numbers. They can be written in the form P over Q, so as a fraction, where P and Q are integers and Q is not equal to 0. Q with a graph after it is a set of irrational numbers, and that includes surds, logarithms, pi, and e. Z is the set of integers, so everywhere from -infinity up to +infinity. And finally, n is a set of natural numbers. That's 0 and then all the positive integers. We can also write things like Z with a little plus above it, and that means just the positive integers. Or we could write it with a plus and a 0, and that will include the 0. And of course, you will recognize that this is the same as the set of natural numbers, n. Now, sets can be finite or infinite. The special number sets that we covered, the complex numbers, the real numbers, the rational numbers, etc., they're all infinite sets. But the set we defined, A, which contained the numbers 1, 2, 3, 4, 5, that's finite. A subset A of a set B contains some or all of the elements of B. And this is what we write. This is the symbol for is a subset of. And so A can't contain any elements that are not in B. So for example, our set A, it's a subset of the set of integers Z. It's actually a proper subset because A is not equal to Z. So we don't need this equality here. We can just write A is a subset of Z. Now there's a specific notation that we use to define a set, and you'll be used to the fact that in the International Baccalaureate courses, it's very particular on notation, so you need to get this right. So we can say that this set is defined as the set of all x such that x has to be less than or equal to 5, where x is a positive integer. Now before we move on, I just want to cover interval notation, because instead of writing A is less than or equal to x is less than or equal to b, for example, which is this diagram here, we can use this shortcut. So in between square brackets, we just write A and B. Now, the brackets point in if we have equality, and we show equality in the diagram with coloured in circles, but they point out if it's not equals to, which you can see here. And in the diagram, that would be an open circle. Okay, moving on. We define the universal set U as the set from which the elements are drawn. So in our previous example, we said that set A was the set of all x such that x is less than or equal to 5, where x is a positive integer. Well, here's the universal set here. It's the positive integers. And we can say that A is a subset of U. Now, the universal set doesn't have to be one of the special sets. We could define it as anything. We could define U as the set of x such that x is less than or equal to 10, where x is a natural number. And we use Venn diagrams to represent sets. What we do is draw a rectangle to represent the universal set, and then within the rectangle, circles represent different sets. And those circles can overlap or they can be disjoint. There are 3 set operations that we're going to cover. They are union, intersection, and complement. The union of 2 sets, A and B, contains every element that exists in A and every element that exists in B, but we don't duplicate them. And we write A union B. Here's an example. If we have the set A, which contains the elements 1, 2, 3, 4, and 5, and set B contains the elements 2, 4, 6, 8, and 10, then A union B would be everything in A and everything in B, but we don't duplicate the 2 and the 4. The intersection of 2 sets A and B contains only the common elements that exist in both sets, and in this case we write A intersection B. Our previous example, A is a set 1, 2, 3, 4, and 5, B is a set 2, 4, 6, 8, 10. The intersection between A and B contains the elements 2 and 4. Now we mentioned disjoint sets earlier. 2 sets are disjoint or mutually exclusive if they contain no elements that are the same, and the circles will not overlap. So for example, if we've got set A, which is elements 1, 2, 3, 4, and 5, and set C, which has elements 6, 7, and 8, they are mutually exclusive or disjoint because there's no elements that are the same. In this case, the union, A union C, is going to be all of the elements and we don't need to worry about duplicates. And the intersection is the null set. The complement of a set A contains all the elements not in set A, and we denote this by A grav. Now recall that Q is a set of rational numbers and Q grav is the set of irrational numbers, and these are complementary sets because there are no common elements. So here's an example. Given our universal set is defined as the numbers less than or equal to 10, where x is a natural number, and here's our set A, let's find the complement of A. So what's in this set that's not here? Well, 0, and then 6, 7, 8, 9, 10. So A grav contains these elements. There are 3 relationships between a set and its complement. Firstly, the intersection between A and the complement of A is the null set because there's no common elements. Secondly, the union between A and its complement must be the universal set. And then finally, the number of elements in A plus the number of elements in the complement of A must equal the number of elements in the universal set. Now we can use set notation to identify various regions in a Venn diagram. So have a look at this first one here. This is everything except for Q. So this is the complement of Q. We write Q grav. Here we have everything except for the intersection between P and Q. So we can put P intersection Q in brackets and then do the complement of that. How about this one? This is everything that is only in Q. Now I like to call this the cookie region because it looks a bit like a cookie with a bite taken out of it. And we can make this out of the complement of P and the set Q. Have a look what happens when I join these two together. So here's the intersection of those two sets, is this green part. Now to write this, we're going to write Q intersection P graph. Last one. What do we have here? We have two cookie regions, don't we? So I'm going to write P intersection Q graph for this one and Q intersection P graph for this one, and then I'm going to join them together and take the union of both of those sets. And don't forget your brackets in this case. There are actually 4 regions that we can identify. So we're fairly confident with this one. That's the intersection between P and Q. We just learnt these two. So P intersection Q graph and Q intersection P graph. And outside here, we have everything outside of these circles. So that's the union, and we want the complement of that union. Now a Venn diagram could show the total number of elements in each region rather than the individual elements, like in this example. Let's find the number of elements in the union of P and Q. So that's everything in P and everything in Q, including the overlap, but don't double up. So it's 4 plus 3 plus 5, which is 12. How about the number of elements in P, but not in Q? So that's just here. So that is 4. And now we want to know the number of elements in the complement of the union between P and Q. So that's everything outside of these two circles. And so that is 3. We'll quickly cover a problem-solving question involving Venn diagrams. The class has 20 students who study Japanese, 13 who study French, 3 who study neither Japanese nor French. If there are 30 students altogether, how many study both Japanese and French? So I'm going to drop a Venn diagram. Start with the rectangle and the 2 circles. Our universal set, of course, is the 30 students. And then we've got the Japanese-speaking students and the French-speaking students. Now, we're told that 3 study neither Japanese nor French, so that goes outside the 2 circles. Now, the way to find the overlap is to add up these 3 numbers, the 20, the 13, and the 3. And if we do that, we get 36, which is more students than we have. And that tells us the overlap. We've double counted by 6 students. That's actually the answer to the question. There are 6 who study both languages. But let's fill in the Venn diagram anyway. So 6 goes in here. Now we know there are 20 students who study Japanese, so that means 14 study only Japanese. There are 13 who study French, and so there are 7 who study only French. And a quick check at the end. 14 and 6 is 20, 27 and 3 is 30, so we're correct. Let's finish off with a past exam question. Consider the following Venn diagrams. We have diagram 1 and diagram 2. Write down an expression in set notation for the shaded region represented by diagram 1. So let's have a look what we've got here. This one's pretty easy, isn't it? It's everything that's not in A. So that's the complement of A. We write A graph. Now what about diagram 2? In this case, we've got everything in C that is not in D. So this is like the cookie region, except we don't have overlapping sets. We've got a subset. So this is going to be everything in C, intersection D graph. So we write C, intersection D graph. Part B, shade on the Venn diagram the region represented by the set H union I. We want the complement of that. Okay, so that's everything outside those circles, isn't it? So let's see if I can do this. We want everything outside these circles and colour in around them. I'm only going to do a rough job. You can get the idea. That'll do. Okay, part B. J intersection K. So that's everything in J that is also in K. That's just going to be the set K, isn't it? Okay, that's it for this lesson. In our next lesson, we're going to cover the laws of probability.